Hello, everyone. Thanks for joining this conference. So actually, it's our second to last conference for the conference cycle of the master on digital twins. So we had a few conferences in the past, more focused on practical applications, people from the industry. And today we welcome Vincent Lepetit from 𝗂𝗵𝘁𝗀𝗃𝗃. So he's a professor at 𝗂𝗵𝘁𝗃𝗃, specialized in computer vision. So the goal of the conference today is to look at things more on the research side, what we can do today with AI, computer vision. So Vincent was a professor at Graz University in Austria before joining 𝗂𝗵𝘁𝗃𝗃. And he got an ERC in 2023 dedicated to the automated construction of digital twins with computer vision. So I think maybe you will speak a little bit about that. Yeah. Okay. So thank you again for attending, and I leave the floor to Vincent. Thank you.
Thank you, Jeremy. Can you hear me online? Is it working well? Okay, apparently nobody complains. Okay, sorry, I would start.
Yes, we can hear you.
Thanks, Vianney. Yeah, so you understood from Jeremy's introduction that I'm a researcher in computer vision. So I will introduce computer vision in general, so in the first few slides, and next I will discuss what computer vision can do for digital twins, and I will explain how AI, so artificial intelligence, fits in the story. So computer vision is something, a very, very general field. So in the sense, or very general, very broad, it's anything that almost anything that you can do with a computer and a digital image. So maybe you have a camera on your laptop, and the laptop could do something with these images. So try to understand. It can be one camera, it can be several cameras. I don't know, for example, if you think about surveillance applications, you can have cameras that are fixed positions at different places. Maybe the images are processed not by a simple laptop, by a full cluster of computer. Maybe you have applications on your cell phone using computer vision already, so using the cameras that you are in on your phone. Maybe the camera is in motion, so maybe on a car, on a robot, on a drone. Maybe it's not just images, but a full video stream. So all these, that's already computer vision. So we are very general. There are many different applications, many different things that can be considered computer vision. And just to make things a little bit more concrete, so I can show you some applications that already actually work. And before I move to actual digital twins. So for example, the applications that you have here, which is car plate reading. So that's there is a camera that capture images of your car, can recognize the plate. So there are many parking lots that are using this system, so that maybe you can pay in the parking lot, and the system assign your ticket with your car plate, and you don't have to use your ticket anymore. The system recognizes automatically your car by reading the car plate, so like a human could do, but except that it's automated. So that's maybe if you pass the speed limit, you can get a fine completely automatically, thanks to the system. So that's thanks to computer vision. You have other applications that are probably older than that because the constraint, the problem is much more constrained. So for example, in factories, if you have a chain if you want to monitor the quality of the products that are built by the factory, so you can imagine something like cameras that are capturing images of what is being manufactured, and as a quality check, which is completely automated. So that would be computer vision. As I said, so I'm sure that you have applications using computer vision on your cell phone. So I'm from Bordeaux, so I took an image of an application that can recognize wine bottles. The idea of the application is that you take an image of the sticker, so the prints that are on the bottle. The system can localize in the image where the bottle is exactly, and match this image with a database of images of all wine bottles, and so that you can get back information for this bottle. So that's just one application of image retrieval, which is part of computer vision, and that's something which is actually very general. You have the same system for recognizing plants, for example, or books, and so on. So that's one more application. And of course, so there is autonomous driving, where the cars use cameras as sensors, not necessarily only cameras, but at least cameras are part of the sensors. And even without going into autonomous driving, you already have cars that use cameras to detect the lanes on a road, try to recognize the speed signals, and so on. So that's already something that exists, even if the car is not completely autonomous. But so this talk, okay, so we'll skip that. But so this talk is not about computer vision in general, but also what we can do for digital twins. So you can probably recognize the beam representation of a building here, and from computer vision, so we can imagine many different applications. So for example, one possible application would be to reconstruct a beam representation of an existing building from images. Maybe we want to check if an existing building matches the beam that was designed by the architect, but using images. So do the images match the beam representation? Maybe we want to update a digital twin, so our beam representation of a building when the building changes. So that's maybe we are talking about not a building, but a construction site, which is always changing. So can we use computer vision to create a digital twin, to update a digital twin of the construction site, so from images? And so there are actually many companies that, if you look on the web, that aim into this direction. So I looked into that. It's not always very clear what they do exactly. They try to do that. There is definitely a need. There is definitely a will from companies wanting to do something like that. It's not always completely clear what are the limitations and what are the actual possibilities of what they do. So what I'm going to do for this presentation is to talk about what I know. So research in computer vision that can be applied to digital twins, and to try to make you feel and to understand what are the possibilities, what are the needs to apply these techniques, and what are the limitations, and what is going to probably being developed in the next few years. So the first thing that probably comes to mind when we talk about computer vision and what can computer vision do for digital twins is to go into 3D reconstruction from images. So this image is a reconstruction of a construction site from directly from images. So it's really a direct application of computer vision. So maybe you already saw this sort of reconstruction. I will give you an idea of how it is done and what are the limitations and what are the current development. So it's not a 3D reconstruction is not yet a BIM or a digital twin, because there are things that are missing. Here, in the first part of the talk, I'm going to talk only about geometry. So of course, a digital twin is not just about 3D geometry, but we are getting there. That's at least we are capturing, well, in the right direction to get a digital twin. So I'll talk first about pure 3D geometry reconstruction. And if you're not familiar with computer vision, maybe you think, and it's actually it's definitely not a bad idea, is that if I want to do some 3D reconstruction, I'm going to capture two images because we have two eyes, and the two eyes of humans that are there also to perceive the world in 3D. And so that if we want to take inspiration from what nature does with our eyes, we could take two pictures. So actually, I took two pictures of the campus from 𝗵𝗵𝗶𝗃, two pictures that are relatively close to each other, so that we can do something like the human brain does to build a 3D reconstruction. So that actually works. So there are many computer vision algorithms, methods that do something like that. But in practice, it's more convenient to use not just two images, but a lot of images, maybe even a video sequence of what we want to reconstruct. So if I want to reconstruct to get a 3D reconstruction of the campus, the buildings, the building where we are actually, of 𝗵𝗵𝗶𝗃, we could take, so maybe with a drone or something like that, a video sequence that capture images all around the building. So that's going to be much more convenient than just two images, because we see much more things, but also because all the reconstruction that we get from images is going to be more accurate. So, and just to be clear, yeah, so that at this stage, so I'm going to detail a little bit what we can do with multiple views to get a 3D reconstruction, but at this stage is just pure 3D geometry, let's say standard computer vision. There is no, I would not call what I'm going to present in the next slides AI, artificial intelligence, so there is no deep learning whatsoever at this stage. So it's going to come in the second part of the talk. So yeah, so let's detail this part. And it's the general idea is pretty simple. So let's imagine that I have two images that are taken relatively far apart from each other. So that's actually the representation of the camera, or maybe the position of the camera when this picture was taken. So it looks like a pyramid, and if you look at papers from computer vision or videos from computer vision, we typically use this type of representation because it's very informative. So you can see where the camera is when it captured the image. And so that's this pyramid, which is a representation, and the top or the tip of the pyramid is called the camera center, and that's going to be useful in the next slides. But this thing, that's a representation of my camera, and that's a representation of where the camera is after it moved and to capture another images of the building that we would like to reconstruct. So what can we do from that? The general idea is in fact pretty simple. So let's say that I know that I'm going to consider this pixel in the image, which if you consider this building, it corresponds to this corner of the building. Let's say that at this stage that I click on this pixel in the image, at the in reality, that's going to be fully automated. But I can also consider the other pixels or the pixel in the other image that correspond to the same corner. And so now you can probably guess what I'm going to do now. You can imagine casting rays from the images, and that's where the camera center is important. So the tip of the pyramid, it's called the camera center, and it has a clear definition in computer vision and in 3D computer vision. But casting a ray in this here, that means starting from this camera center, going through this pixel, and then you get a line. So you can imagine a line in 3D. And so if I do the same in the other image, if my estimation for the camera poses are correct, then the two rays will intersect in the same 3D location. So that's called triangulation. So maybe you know that under the name triangulation, and you get already a 3D point from that. And then you can do the same for other points. That I did it for the other corner, and we get something like that. So that should give you an idea of how we can get some 3D information from images. But be careful. So that maybe my presentation making sound simple, but that's definitely not simple, because what is missing also in this explanation is that we also need to know the position of the camera and the camera. So it's mathematically it's defined as a 3D translation, so for the position, and a 3D rotation for how the camera is oriented. And so you can imagine that, or you can think that maybe we can use a GPS sensor to find where the camera is, but a GPS is nowhere accurate enough to get a good position. So that's actually we are going to use computer vision. So computer vision is self-reliant there to estimate so here what we need really is the motion of the camera between these two images. So that's defined as a rigid motion, so one 3D rotation and one 3D translation. And to get to this motion, the mathematics are definitely not trivial. The good news is that it's a problem which is almost solved. So that's something that people have been working on for actually even before computers existed. So the maths are not easy, but they are done. You have books, reference books, where you can read the theory. I put some equations to illustrate that there is math behind. I'm not going to detail these equations, just for the illustration. And beyond the books, we actually have softwares that do this sort of thing. So typically in academia, we use 𝗀𝗵𝘁, which is completely free, which is convenient, that we can manipulate a lot. But there are actually a lot of other software that can do that completely automatically for you. So when I presented the idea, I said that, okay, we click on these two pixels. In fact, everything is automated. The computers are now able to realize that, okay, so this pixel in this image correspond to this pixel in the image, and can do that automatically for many pixels, for many images. So the system is almost you just have to press a button and you get something. And it's actually pretty easy to use. Maybe you need a little bit of experience to capture a video sequence so that it works well, but this thing is pretty stable. And maybe, yeah, so one thing, so that's I present that as computer vision. Maybe you already know about photogrammetry, and you are thinking thinking that it's pretty close to photogrammetry. It's not just pretty close, it's exactly the same concept. So it's more a matter of history and community. So photogrammetry is, as I said, it's older than computers. People, when the cameras were invented, they realized that they could do 3D stuff with that. And you can actually, so from this drawing from, so one of the fathers of photogrammetry, they were doing exactly the same math. So it's the same concept, is just different community. What computer vision brings is that we can do matching of points between images automatically, but otherwise the maths are pretty much the same. And yeah, to show you a concrete example, so that's definitely not something new. I think this video is almost 10 years old, maybe even more. I will just stop the video. That's if I can. Okay, so that's probably, yeah, and that's going to be more convenient. So as I said, so we can recover 3D points, but also the position of the camera, or the positions of the camera by point matching across images. So this 3D model of the church, so maybe you can recognize it's I think it's the church from Lausanne in Switzerland. So the video was created, or the 3D model was created by capturing images from a drone. The drone rotates around the church, capture images, and then there is a software that finds correspondences between points. And if you look carefully, you can actually see the points. It's just that there is a lot of them. And so because there are so many of these points, it looks almost dense, like a surface. But in fact, it's not a surface, it's really points. Try to find images where we can see that a little bit more. So you can see that there are holes. And in fact, it's really the points that have been reconstructed automatically by the system. And we get 3D shape. So it's, I would not necessarily call that a digital twin of the church, but it's getting there. And that's here, that's the same for a bridge. And you can actually see there the images, so you can recognize the pyramid that is used to represent where the camera was when it took the picture. So there are many pictures taken of the bridge, so from again, so from a drone, and you can understand that actually it's not just 2 images that were used to reconstruct this point, but many images. So when you put all that together, so that you can get a pretty accurate 3D reconstruction, and from that you can imagine a lot of different applications. Maybe not yet a digital twin again, but so here. That's a picture that looks like it's a satellite picture, but I think they simply took images from a drone and put the images, or all the images, into a 3D model, and then you can visualize the 3D model from above, even if you don't have a satellite, for example. Then you can measure stuff. You get a surface model. You can, once you have the 3D representation, so the 3D reconstruction, you can imagine different applications. So that's from that, it's pretty easy. So that's I guess you can call that a digital twin of an accident, but that's also a 3D reconstruction. So this thing, it's pretty stable. All these techniques, so these feature points, they are done their software. And just to show you something which is much more recent, but still pure research, I would say, just to give you an idea of what is coming. That's okay. Maybe the best thing is to show you the video. So the video is actually a video of a 3D model that has been reconstructed. So you can imagine, so there is a pond, so nobody could go into the pond to capture images. So that's images that are taken from around the pond. And that's the rendering of the 3D model. And I have to say that it's pretty good. And I will play the video, and from the video you will understand how it's done. So it's not completely points anymore. It's, and I would say, an extension of what I just presented. Again, so it's really research at this stage, but it's starting to be very, very popular. And I will play the video because until the end, because from the end, you will see the limits. And yeah, so here, so that's so the system does not know about reflections and so on. So it just imagine that there is something symmetrical inside the below the pond. So just reconstructed that correspond to the reflection of the house. But okay, that's the end of the video is also interesting because here what is used is not just points. So before it was really points in the geometric mathematical sense of the term, just 0D points. Here it's we are using elongated or Gaussians, so to basically to stretch and to get 20 points that are that cover more of the geometry. And that's something which is very powerful in terms of rendering. It's pretty beautiful. And one thing which is interesting also is that because it's not points anymore, but something which is more spread over space, we can actually extract a 3D surface. So that's what we did recently. So that's here, that's an image which is a rendering of the 3D model, and that's a view of the 3D mesh that we can extract from images. So there is no, it's just a pure images. And this surface, so if you are familiar maybe with CAD models or maybe even BIM models, they are made of triangles. So it's really something which is dense. It's not points anymore. And once you have that, you can manipulate the scenes because you have a mesh or surface-based representation of the scene. So that's so the one part of the mesh from the one scene is put into another scene. So maybe that's not necessarily very useful for digital twins, but it's a way to show that we actually have a 3D representation of the world created from images which can be manipulated. Okay. And so everything I presented so far, that assumes that the scene is static. That means that it should not move. So if there is something small that moves when I capture images, so for example, if I have a drone, capture images, there is somebody walking in the scene. If it's a small part of the scene, everything is robust to these sort of things, and it's not a big big deal. But maybe we are also interested in dealing with dynamic scenes. So, for example, we are starting to work with construction sites, and which are always dynamic, always moving. You can probably not ask people to stop working to capture a 3D scene, and maybe you want to capture how objects move for the digital twin. So if you want something which is kept up to date, so we're starting to working on that. So it's really so I put work in progress. Is just to give you an idea of where the research is at this stage. But so that's a video that we are going to use as input. So now you see so it's a very simple scene, but it's not static. It's dynamic in the sense that there are the box is opening during the video. So of course it's synthetic and so on. But the problem here is that it's dynamic, and we'd like to get a 3D model, a 3D representation of this, but including the joints, including how the model, the box opens. So here it's a box. With a little bit of imagination, you can think about other objects. I don't know, a crane on a construction site, a truck or something, or a tool which is actually articulated. And so that's the kind of results that we get. So what I show here is visualization of what we captured, but from new points of view. So to show that we actually captured the fact that the object is opening with these two joints. And so that's again, so that's a very simple problem, but a very simple video, but that's just the beginning of the work on this sort of stuff. So I said that this field, so pure 3D reconstruction, is pretty mature. So it's definitely true. There is still some limits in the sense that if you look at this 3D model, for example, because it's based on 3D points, the model cannot be perfect. So it's a little bit weird. So here it's probably something which is just a long bar, which is actually not reconstructed perfectly. It's discontinuous because there are parts that were not missing, that were not reconstructed because it was too thin, too thin in the images. Here it's also a bit weird. Here, the typical artifact is that, so these things are probably on a line. And if you ask a designer to reconstruct a 3D model, the human designer will naturally put lines, straight lines where there are straight lines in the scene. Here, in what I presented, because it's made of points, you have no guarantee that it's a nice straight line. So we are working a little bit on that, but there are very limited work to make this thing improved. So that's still limitation, so which can be a problem or not, depending on what you want to do exactly. So okay, so this part was really about 3D geometry. Again, there is no AI yet, and we'll try to explain where AI is needed to really go further than beyond just a pure 3D geometry. So the first thing, what I will use to introduce AI is to consider 3D reconstruction from single view. So in fact, you probably realize that, okay, we have two eyes, but if you close one eye, you still have a pretty good perception of a scene. So in fact, there is something that we can do from a single view. What I like to show my students when they start computer vision is a video like that. So if I show you this image, you can probably have a good idea of the 3D shape of this object, right? And of course, that if I show it, is that there is a trick. It's actually not like that. It's just because, so the object is made so that just to fool your visual system. So what happens? So that's given a single image, there are actually, of course, many 3D shapes that can generate this image. So if you look at an image this image, it looks like an image of a cube. So it's maybe actually an image of a small cube, which is close to the camera, maybe a large cube, which is farther away from the camera, but actually it can be any shape. So, not any shape, but many different shapes. So if you are careful, you can design a shape which is a bit weird that can generate this image. So that means that from a single image, we cannot infer formally the 3D shape that generated this shape, that generated this image, except that most of the time, if we think that when we look at that, we think it's a cube, it's very likely that it's a cube. So it's just because with the experience that we acquired, even if it's not mathematically possible to be sure that it's a cube, 99.999% of the time, it's going to be a cube. And that we get that just because from our experience, since we were a child or baby, looking at the world, moving into the world. So actually, we can learn something about the world that we can use to infer stuff from images. And it's really impressive. So if I go back to this image, so that is just because these things look like orthogonal stuff, parallel stuff, that we can get a 3D reconstruction, and you do that instantly. So that's something amazing. So here it was designed to fool you, but most of the time, but really a lot, that works very well. But so we would like to have something like that. If we want to do something which is as good, maybe even better than human vision, we need these sort of things. And so that's where AI comes into the game to go beyond pure 3D geometry. And so the one first example that I can show you of which is really AI and computer vision is that it's actually possible to train a deep network that takes as input a color image. So that's what I showed is here. You give this image to a deep network as input, and you get as output what is called the depth map. So that means that for each pixel of this image, you get the distance from the camera to these to the 3D point that correspond to these pixels. So there is several caveats, but I will discuss that later. So I'm not going to detail or explain what is a deep network. Maybe you already know, maybe you probably have some idea. That's just something that relies on actually simple operations, so additions, multiplications, really simple stuff, but really a lot of them. So that's, and when you combine a lot of multiplication, addition on the values of this image, you can create something which is pretty complex. But let's just say that it's a deep network is a black box that takes something as input and take something else as output. So for this network in particular, so that's something that there are many deep network or many researchers working on this problem. So I took what is the most recent thing about that. So what they did is to take something like 1.5 million images used as training data. So what does it mean? Is that they have a data set of an image, so color image, and the depth map that correspond to this image. So obtained by some other mean. But so that means that now they have examples that what they have as input, so color image, and what they want as output, so a depth map. And it happens that with deep learning, if you have a lot of these pairs, you can train a deep network that takes the one input, so a color image, and predict the type of output that you want. But okay, it's not completely magic. You need a lot of data. And this data is definitely not easy to get because it's not just images, it's also depth maps. But once you have that, you can get. So this network actually exists now. It's if you know a little bit of Python, you can actually download it and use it to apply to your own images. So there is something which is there is a catch here. We don't really know what is the scale of the depth map in the sense that we don't really know if it's this pixel is 10 meters away from the camera or 5 meters or 5 centimeters if it's a scale model, but at least so it's the depth map is defined up to scale. Just to say that you can get the same type of data from other sensors. So here that's a camera plus a deep network. You probably know that there are LiDARs that do something similar. There is something called RGBD camera that capture also images and give you a depth map, but these sensors are active sensors in the sense of a LiDAR, for example, send a laser to get the depth. So then it's a trade-off. You can use maybe just only a camera and a deep network, maybe a camera and a LiDAR. So it depends on your application. A LiDAR is probably more expensive, maybe a little bit more heavy, but yeah, so depending on the application, you can use these different sort of sensors if you want to have something in 3D like that. But there is something that these sensors cannot do and that a camera can do, and that's the limits of the 3D geometry. So that's what I presented in the first part is what you get is a 3D model, which I would call unstructured in the sense that there are just points. And for example, a point on this car for the system has exactly, oh, it's the same type of things than a pixel on the roof or a pixel on the wall. So it's really, it's unstructured. You don't have information which is attached. It's only the pure geometry. While for a digital twin, you know that we would like something which is more high level. So for example, in a BIM model, you can distinguish the walls, the different parts. And so and that's something that we call semantics in computer vision. So that's not, I don't really like the term, but just maybe to sound smart, but it's okay. So that it's called semantics. So it's like that. I will call it semantic. But you would from a digital twin, a BIM model, you don't want just the geometry. You want something. You want to know that this part of your 3D model is, for example, a window. This part is a pipe, this part is maybe a sofa. So that's, and not just the fact that all the points that are on the sofa should be, you should know that it's the part, it's a sofa, all the points together. And so that's where AI and computer vision becomes useful. So I will try to give you an idea before the end of the talk. So let's say that I have already a 3D reconstruction of a room. So I'm showing you data that we use in academia. So that's maybe not a direct link with digital twins in the industry, but in principle, it's the same. So here it's a classroom. It could be a factory or something else. But let's say that I already have a 3D model of what I am interested in. So there is it's just the geometry. If I want to understand or to label this 3D model with the objects that are in this 3D model, then I can train another deep network, for example. So that's a possible approach. That would take, so this deep network would take some part of the 3D geometry, for example. So so be careful with this representation. So this time it's not an image, it's really a set of 3D points or a 3D mesh. So that can be something like that, but something to represent the 3D reconstruction, so the 3D geometry. It happens that's also why deep networks are very powerful. So you can have many different types of input and output. So here, the input is a 3D reconstruction. What we would like in this case is maybe as output 3D box, so maybe the corners, the position of the corners of the 3D box to tell you, okay, so inside this box there is a chair, and maybe tell you what is the 3D shape of the chair. And so it's possible to have a network that works like that. The caveat is that we do need some training data to train this network. And in practice, so that means that if we want to do the same as before, we would like to have pairs of 3D geometry and the 3D box that correspond to this 3D geometry. And that's not very easy to get. One possible thing to do is to use synthetic data. So that means that starting for 3D models, generating from these 3D models the 3D geometry that would correspond to a capture of this 3D model, and then tell the system that's okay. So what I want as output is the 3D model that was used to generate the first data. So here there is a lot of recipes to make the synthetic data look like what would be during the actual use of the deep network. And plus, using synthetic data, it kind of works, but not very well. So you have to do stuff in addition to just that. But I just want to give you a general idea of what is possible to do with deep learning for this type of problem. And so we work on that. So we went a little bit beyond just pure using a deep network to get this type of output, but I will just show you the results. So the input to our system is a scan, so a 3D reconstruction that looks like that. And we can get a 3D reconstruction. So here we detect where the objects are in the scene, and we put a 3D model that corresponds more or less to the object that is in the scene. And we do this. So we do the same for the walls of the scene. So that's what you see in red. So that's getting closer to a digital twin in the sense that we have a representation, a semantic, as we say in computer vision, semantic representation of the scene. So here it's tables and chairs and so on, because that's what we work in academia. But you can imagine that it could be, I don't know, trucks, pipes, or whatever you are interested in your system. I will skip that. Maybe I will show you that just to show that we can do something similar for dynamic scenes. Here, the problem, in a way, the problem is much simpler because we know that we are looking at two hands and a box, not a box, but we know the 3D model of the object, but we get a 3D, which you could call a digital twin, a 3D representation of the what is going on in the image, where where the hands are, where the object is. So it's dynamic, so it's a little bit more difficult than what I presented, but it's also easier in the sense that we know what we are looking at. It's much less general than before. But at least, yeah, we can also deal with dynamic scenes. And maybe so one thing to conclude on that and to have a complete story. What I presented so far is that it's with images that were captured by humans. And it's better to be an expert or to have some experience in capturing the videos that you want to use for reconstruction. So it works well, but it's better to know what you are doing. Maybe make sure that you capture everything in the scene. So that would be very nice to capture these images automatically. So, for example, let's say that you want to capture a digital twin or 3D model of a bridge. If you give me the drone will crash in the next 5 minutes. It can be very difficult. You know, you have to capture the pillars and so on. So that would be very nice to have a system that can do the capture automatically. So that's worth working on that. So that's currently it's purely in simulation. So that means that it's much simpler, but you can do something. It's relatively easy to do 90% of the job with some heuristics. If you are a good engineer, I'm sure that the good engineer will come up with something, but to make sure that the system will cover everything, so 100% of the scene, and do that in an efficient way, it's actually a very difficult problem. That's why we're just starting working on that. So but it does some cool videos. Okay, so maybe just to conclude, so that's I hope I was not too long. So there are many different things that computer vision can do for digital twins or BIM models. So in terms of 3D geometry, as I said, so it's an old problem. Not necessarily, or it's not an easy problem, but it's now almost solved in the sense that you have a lot of software that can actually do that for you already. There is still a little bit of research on that just to make things more robust, but we are pretty done over there. Getting the 3D semantics from images, so that if you remember the videos with the chairs, the sofa, the walls, which could be, I don't know, some tools in your factory, it's still research. The main problem, the main issue is to be able to adapt to new scenes where we don't really know the objects. So we did something for chairs because we have data. If you want to move to do the same thing in a factory, it's getting there. Researchers are working on the problem, but it's definitely not the maturity of this software that can do a 3D reconstruction. And the last brick of the systems to get this digital twin would be something which would be very nice, is to do the automatic capture of images. I'm pretty sure that we can do something so people can hack something to get that would work on some easy scenes. To have something which is completely general, I think that's still a bit difficult. But we are working on that. Okay, so I will stop here. So that's the PhD students who did the actual work. I'm just presenting it, and I hope I was not too long. And I will end the presentation. And I'm happy to answer questions if you have any. Thank you. Thanks.
Okay, so if you have any questions, please you can ask them. I don't know if we have some in the room. Yes.
I have a question concerning the method that you presented before you introduced AI. You use different views to construct the 3D image. From a simulation point of view, is there like a parameter that like is directly related to the precision of the image? Size or the number of pixels, number of points?
Yeah, so you mean the accuracy of the 3D model that you can get? It's very difficult to give you a good answer. There is no general answer. I'm pretty sure the software can give you some estimate of the error, but it depends a lot on the trajectory. The type of 3D scene that you want to reconstruct. So of course, the resolution of the images is important, because if you have nice resolution, high resolution images, things are going to be more accurate. But imagine that if you, so for example, for the triangulation, the configuration is nice, is like that. That's because that's where the intersection is more accurate. So it depends on the trajectory, what you are looking on. So there is no definitive answer. There is no rule of thumb. But anyway, so that you are going to, if your reconstruction is screwed, you will see it very quickly. Otherwise, it can be very accurate. So that's with a little bit of experience, then everything is well calibrated, and you can get, I don't know. So you see for the cathedral, it's a few centimeters, which is very impressive for a large building.
Thank you.
We have some questions online, or?
Yeah,
Okay. Maybe I was wondering about the dynamic scenes. Is it do you need that the typical time scale of the movements inside the image to be much larger than the frame rate or something like that?
It's different. So actually, we prefer to have slow motions, and so probably so if you have a high speed camera, things will be easier because the motion is much smaller. So you can start tracking. So that's definitely be so that So if you have a high speed camera, things would be easier. And what we like is also to have, so in computer vision, to have stuff on what we are interested in. So for example, if you have a white wall, so that's it's very difficult to reconstruct because everything is white. So all the points are white. If you have something, okay, so that's people online cannot see the floor, but if you have, I don't know if it's the floor is made of wood or something like that, that's going to be much easier to match points across images. And so if you have a little bit of stuff and high-speed camera, then it's easy to track. If you have a lot of stuff on your surfaces, but the motion is still fast, then it's you can still keep track of stuff across images. Then if you have not much texture, so not much stuff, a slow camera, then things are getting challenging. That's but everything is mostly about matching stuff across images. So maybe the hands across images, maybe points and stuff like that.
And are there already people using that for transport in the city to know where people are going, for instance, detecting cars, bicycles, etc.?
Yes, so definitely. So long-term object tracking. So, for example, across, so if you have surveillance cameras or cameras that are in fixed position, so relocalization or recognition of people that you saw from one camera to another, that's also an important topic in computer vision, definitely. So that I'm talking about people, but that could be cars, vehicles, or whatever, to recognize that, okay, so this person that I saw in this camera, that's now they are there in this other camera, and that's definitely a topic in computer vision.
Just a question about the size of all this technology. What kind of computer do you need
to do training? So typically deep learning, you need some training, and there it's good to have a server, a computer server to do the training.
And for instance, for the 1.5 million images, the training.
Yes, the training. I think it's at least several days. That's yeah. So it's but then once it's also the advantage of what is nice with deep learning. Once it's trained, then you can do the inference. Yeah, it could run on my laptop. Yeah. Exactly. It would be very fast, and you adjust a laptop is sufficient. And that's definitely convenient for applications. Yeah.
Yeah, especially if you need some real-time.
Exactly. Yeah.
You have real-time data coming.
Yeah. So that's yeah. So they use a GPU. They are going to run on GPUs. The GPUs are fast. So it's not necessarily real-time in the sense that 25 images per second, but it's 10 images per second without doing anything special. So that's which is something very impressive and very, very convenient. Yeah, definitely.
I don't know if you have people online we have to monitor. Feel free to open the microphone.
Okay, so I don't know if we don't have any questions. I think we can thank Vincent again for this nice presentation, and thank you all for attending, and see you soon in June for the last conference of this year. Thank you again.
Thank you again, Vincent. Thank you. Bye.